Hey guys, today I'll be talking about AP Physics 1 2024 exam on question 3. So what we have here is the left hand of a uniform beam of mass m and length l is attached to a wall by a hinge, shown in figure 1. The one end of the string with negligible mass is attached to the right end of the beam and the other end is attached to the wall above the hinge at point 1. The beam remains horizontal and the hinge exerts a force on the beam of magnitude Fh, and the angle between the beam and the string is theta equals theta 1. The following rectangle represents the. Okay, so you're supposed to do a free body diagram here on the beam. So, first of all, what you have is you have the force of gravity. The force of gravity always starts from the middle of the beam. So, this would be equal to Fg. Next off, we have the string force or the tension force, and that would be going in this direction with an angle theta 1 to the perpendicular to the horizontal. And this can't be all, because if this is all, then the beam would just rotate counterclockwise. So there must be another force counteracting the tension force and the gravity force, and that would be the wall force the wall exerts on the beam, and we could call that the reaction force, so Fr, and this would be called Ft. Okay, the string is then attached lower onto the wall at point 2, and the beam remains horizontal as shown in figure 2. The angle between the beam and the string is theta equals theta 2, and the dashed line represents the string shown in figure 1. The magnitude of the tension in the string in figure 1 is Ft1, and the magnitude in the string of shown in figure 2 is Ft2. Indicate which of the following correctly compares Ft2 with Ft1. Okay, what I made here is an axis, and this basically shows the distribution of the tension of the string. So for the second tension, the vertical component is lower, because since the angle is lower, this vertical component of the tension will be lower. And the vertical tension of number 1 would be higher. So since the beam must maintain a constant vertical tension, which means a constant vertical torque, uh, the overall tension this in string number 2 must be greater to make this vertical component of the tension be greater as well. So I would write that down. So the tension in T2 would be greater, and this is because when the string has a lower angle with the beam, the vertical component of the tension, the vertical component of the tension decreases. So the whole tension, the overall tension must increase to bring that the vertical component of the tension back up to counteract the other forces or the other torques. Starting with Newton's second law in rotational form, derive an expression for the magnitude of the tension in the string. Express your answers in terms of m, theta, and physical constants as appropriate. Okay. So begin your derivation by writing a fundamental physics principle or an equation from the reference book. So first of all, we have the equation. Newton's second law states that the net torque is equal to the momentum times the angular acceleration. Um, yeah, okay. So now, since we know that the net torque is equal to zero because the the um okay, Newton's second law in rotational form states that the net torque is equal to the angular acceleration, the net the angular acceleration of the system times the rotational inertia of the system, which is uh how much it resists torque being applied. And now we know that net torque equals zero. This is because the net torque, the beam is not moving, it's not being rotated, so T net would be equal to zero. Since we know that the inertia of the system is a non-zero number, the inertia can never be equal to zero. That means that the acceleration, the total net acceleration equals zero. Now, we need to derive an expression for the magnitude of the tension. So since we know that the acceleration of the system or the net torque is equal to zero, that means that we can derive an expression for the net torque and set it to zero. And that contains the tension force. So the net torque would be equal to, now, since we don't know the reaction force from the wall, because there is a force here called Fr, we would start from this distance. So we would call this d equals zero. This is because no matter what the force of the reaction is, the net torque of that would be zero if we're starting from here. So all we need to worry about is the gravity force and the tension force, which we need. So the gravity force has a distance of L over 2, and the tension force has a distance of L. So the net torque would be equal to the torque from gravity plus, uh, sorry, the torque of gravity should, yeah, sorry, the torque of gravity plus the torque of tension. And what would the torque of gravity be? Well, it would be force of gravity, which is m times negative g because it's going down. So m times negative g times the length, which is L over 2. So negative mg times L over 2 plus the torque of the tension would be equal to the force of the tension times the distance, which is L. And we can set the net torque to be equal to zero as we found out over here. So just rearranging this, we get Ft times L equals Ft times L minus mg L over 2 equals 0. Now we need to find Ft. So we rearrange it. mg L over 2 equals ft times L. And then we can cross out L on both sides, and we get mg over 2 equals ft. Is your derived equation in part C consistent with your justification in part B? And explain your reasoning. Oh, one more thing. For torque, you can't just do the net torque. Sorry, for the tension torque, you can't just do the total tension, because the total tension is, we need to take in account for only the vertical one. The vertical component is equal to, if this is theta, then the vertical component would be equal to F times T times sine theta, because it is only the vertical component that exerts a torque. The horizontal component does not exert any net torque. So in this case, F times T times L times theta, sine theta, sine theta, and it's over 2 sine theta. And is your derived equation consistent? Yes, because as sine theta decreases, that means as theta decreases, sine theta decreases as well, which ultimately results in the force of the tension increasing. So you could just write that. As the angle theta decreases, the sine theta decreases, and from my formula, sine theta is inversely proportional to the force of the tension in the string. So when sine theta decreases, the tension ultimately increases. And that would be my answer for that. The string is cut and the beam begins to rotate about the hinge with a negligible friction. On the following axis, sketch the angular speed of the beam as a function of time for the time interval while the beam falls out, but before the beam becomes vertical. So what happens here is when this is released, the original angular speed will be very great, because the force of gravity, the torque exerted by the force of gravity is perpendicular to the thing. But as it goes down, like pretend the position is here and this is the beam, the force of gravity is not perpendicular to the beam. So the torque would actually only be this component of the force of gravity, which is less. So later, as it goes down, the angular speed would decrease. So it would look something like this. So initially, the angular speed will be up, and it will decrease over time. And that would be all for this question. Thank you for listening.